Number 2 is a fairly long problem because there are 5 different sections to it, so bear with me. I'm assuming you have downloaded your formula sheet off of my class page, and we'll be referring to that periodically. So, in number 2, as a gun is fired, the bullet accelerates the length of the 1 meter barrel and gains a speed of 899.2 meters per second. So we have 1 meter is, of course, the distance that it's going to accelerate, and we gain a speed of 899.2 meters per second. So if we're gaining that speed, of course, that's my final velocity. That would make my initial velocity 0 because bullets aren't traveling too fast before you pull the trigger. So that would work for that. The first one we want to do is find acceleration. So if we're looking for A, the A formula that has those 3 in it is found the third formula down from the top. And that would be VF squared minus VI squared divided by 2D. So my VF we said was 899.2 squared divided by 0, or minus 0, and then divided by 2 and divided by 1. So if we do this correctly, we get 404,280, which of course after rounding would be 404,000 meters per second. So this would be the acceleration. Now don't freak out when you get a huge number because bullets accelerate super duper duper fast after you pull the trigger, and so you should get a big number. That shouldn't be a major surprise. If we move on to part B, in part B we asked if the bullet's mass is 5.97 grams, that's the mass, how much force was there? Well, this is the mass, but we need to change our mass to kilograms. So if we change it to kilograms, the mass goes from grams to kilo. That's 1,000 bigger. This will get 1,000 smaller. So that'll be 0.00597 would be the mass that we need to put in. So all we're going to have to do is say, what is the force? Well, F equals ma. So my F, of course, is 0.00597. And the A is the 404,000 that we just got from right there. And so if we plug that in, times after rounding, we end up with 2410 newtons. So that's how much force the gun pushes the bullet with, and of course that's how much force the bullet pushes the gun with, the opposite direction, which is why the gun reaches out and gives you a little love tap after you shoot it. In part C, we want to know how long did it take for the bullet to leave the gun. So again, understanding the values that we had up on top, these top values, and knowing that this is our A over here, we can figure out, well, the easiest formula to use is, let's ignore the D and use the VI and the VF and the A to solve for T. To do this, we're going to use the equation that's way at the top left corner. That says VF equals VI plus AT. Well, my VI is 0, so this part's going to go away. So if I'm looking for T, obviously the A is just going to come down and hang out underneath over there. So to find the time that's in the gun, all I need to know is the final speed was 899.2, and the acceleration was, of course, our 404,000. And if we divide those two numbers, we find we get the massive number 0.00223 seconds, which of course is a very tiny time, but how long do you expect a bullet to hang out inside the gun after you've pulled the trigger? It's going to be a very tiny time period. So these three, the A, B, C, all happen inside the gun, and since it does happen inside the gun, the answer from part A gets used in part B, and it gets used in part C. And so that A happens there because that is the acceleration that's happening inside the gun. However, when we switch to part D, when we're switching to part D, what's happening is the rifle is fired straight up. How high will the bullet go? So some things are different here. What's happening is now the 899.2, which was the speed that it left the gun with, so that, or excuse me, that was the speed that was at the end of the gun, so the initial speed was 0 and it went to 899.2. Now that we're in the air, that becomes the initial speed in the air. So this is now the V initial. And if I'm shooting this bullet straight up, I know that my V final is going to end up being 0. And so they kind of switch places. So I'm going to shoot it and it's going to go straight up until it stops going. My acceleration here is not going to be that huge number. If I stick in that huge number, all I'm going to get is the length of the gun. I'm not looking for that. After it leaves the gun, my acceleration is just going to be gravity. So gravity is going to be what's slowing me down. So I'm going to have that acceleration. So again, I have VI, VF, and A, and I'm asking for how high it goes. So I'm looking for a D. So what we're going to do is we're going to use this same equation that we used in part A, but the D down at the bottom and the A over on the other side, they're going to trade places. So if they trade places like that, we're going to end up with D equals VF squared minus VI squared over 2A. And again, we know all the numbers, so this is cake. So it's going to be 0 squared minus 899.2 squared divided by 2 and divided by 9.81. So if we plug that correctly into my calculator, we get divided by 41211. So after rounding, of course, that's going to be 41200 meters. So that's going to go up quite a ways, 41,200 meters up in the air. And of course, we're ignoring air resistance. In real life, it wouldn't quite get that high. It still gets pretty high. In part E, what we're going to do is we're going to say the gun is pointed at a 68.3 degree angle. How far will the bullet travel? Well, of course, now suddenly the bullet is in a nice parabolic trajectory. It's going to land at the same height it took off from. So we can just use our range equation. So that's going to be sine 2 theta v squared over g. So I'm going to take the sine of, and then inside the parentheses, make sure you do 2 times the angle, which in this case was 68.3, times the v, which again is the bullet's velocity, 899.2. Make sure that that gets squared, and then we divide by 9.81. So if we say sine 2 times 68.3 times 899.2 squared divided by 9.81, that gives me a whopping 5,6. Let's just round it right now. The first 3 we keep, 566. Everything else turns into a 0. So that's 56,600 meters. Huge distance. Of course, with air resistance, it wouldn't go that far, but it would still go ridiculously far. You want to be careful when you're shooting guns up in the air. So again, to recap in problem number 2, we find the acceleration in A, and we use that in B and C. But we cannot use that same acceleration in D and E, because in D and E it's happening outside the gun. In A, B, and C it was happening inside the gun. So inside the gun we had that huge acceleration. Outside the gun we have just 9.81 as our acceleration. So the 899.2 in A, B, and C was the final speed, because the final speed at the end of the gun was that number. But then in D and E, that's the initial speed going into the air. So to celebrate, we have a picture of the day today. I took this last week. Isn't he pretty? See ya.